Chapter 6, Number 17. When a 9.09 kilogram mass is placed on top of a vertical spring, the spring compresses 4.18 centimeters. Find the force constant of the spring. So we start off, as always, with our picture. So here we go, and our spring is vertically oriented, so it goes like this. And then there's a platform on top of it, I guess, on which we put the mass, the object, M. In so doing, the spring is compressed some amount, lowers some amount, like that, and of course there's still the mass hanging out, and we are told that it goes through some distance S. All right, I'm calling it S. In this case, we have that S is 4.18 centimeters, and M is 9.08, and what we're looking for is the spring constant K, the force constant. We are assumed that it is that it lowers gracefully. If you were to just release it, it actually would overshoot, and we wouldn't know what this compression is, but we're really saying that to support this mass, the spring must be compressed this distance. So let's look at what's going on with the mass itself. There's certainly gravity pulling it down, S sub g. And now there is essentially the normal from the platform, which is the same as the spring force pushing up. And from the free body diagram, we get that the sum of the forces is the spring force minus the weight. And then from Newton's second law, we have the sum of the forces is the mass times the acceleration, which is 0. Again, the assumption here is that this has come to rest to support it. If you were to just release this, it would get to this equilibrium point but overshoot. This would be where it was unaccelerated. We're assuming that the distance given here is where it is unaccelerated. All right, so then we just put them together, and we say the spring force minus the weight is 0. So the spring force equals the weight, but we know that the spring force is K times S, and we know that the weight is M times G. So we can solve for K as being just mg over the distance. So 9.09 kilograms times 9.81 meters per second square, all over, and we have to be careful here, 4.18 centimeters, but if we want the spring constant in newtons per meter, we should convert this and say there is 1 meter per 100 centimeters. And we get 2133.3 newtons per meter. We seem to have 3 sig figs, and so we get 2130 newtons per meter. In his inimitable way, Walker instead writes that as 2.13 kilonewtons, which is fine.